Happy learning! Today we're going to talk about bipartite graphs. All right, so let's start by defining what a bipartite graph is. A graph G, which has a vertex set and an edge set, is called bipartite if the idea is we're going to take our vertex set and split it up into two distinct groups, hence the term bipartite, two parts. All right, so if the vertices can be partitioned, that means we're separating them into two groups. So into two sets. There's going to be a set that we call X and a set that we call Y. So that, well, first, X and Y have no vertices in common. Next, every vertex is either an X or an Y. And finally, every edge has one of its endpoints in X and the other one in Y. Okay, so we're going to use bipartite graphs to model situations where we have two distinct groups. So for instance, if we had a bunch of employees and a bunch of tasks that needed to be complete, maybe the X set would represent the vertices, would be the employees, and the Y set would be the tasks. Okay, and then like an edge would mean like this employee has the skills to complete this task, something like that. All right, so let me get you an example here. So if we have the following graph, this graph here is a bipartite graph. Okay, maybe it's not immediately obvious. It will become obvious. Maybe it's not immediately obvious to you. But look, if we let X equal ABC, and we let Y be DEF, we could see that all three of the conditions are satisfied. Right? There's no overlap in these two sets. Every vertex is either an X or it's in Y. And then we could check there's no edge that goes from X to X or Y to Y. Every edge has one of its endpoints in X and the other one in Y. Okay, so this is a bipartite graph. Okay, another example is suppose we had some clubs on campus that wanted to reserve a room. Okay, certain rooms would fit for certain clubs and not all rooms would fit for all clubs. All right, and so suppose we had 4 rooms So this would be room 105, room 201, room 271, and room 372. All right, so suppose these are 4 of the rooms on campus where a club could meet, and suppose we had 3 clubs. Math, chess, and art. Any chess players watching this video, let me know in the comments if you play chess. And if you do, I'm happy to play you on chess.com. Okay, so we can model compatibility between rooms and clubs using a bipartite graph, right? So suppose math only works in room 201 or 372. We could have these edges represent compatibility. Okay, so this is saying math is compatible with those 2 rooms. So we could put the math club in one of those 2 rooms. And maybe chess likes this room or this room. And maybe art likes this room, this room, this room. Actually, art likes them all. Okay, so this is a bipartite graph, and it could be used to model this relation between 2 distinct groups, clubs and rooms. All right, let's do one more example. All right, so try this one before I answer it for you. Is the following bipartite? And then if yes, partition the vertices. Meaning what is our x set, what is our y set. All right, what is our graph? Our graph is this. All right, so is this a bipartite graph? I'll give you a hint. It's not drawn like a bipartite graph at this point, right? Because if traditionally we'd have like our x set be the top vertices and the y set be the bottom ones, but here we have edges from x to x. But can we move around the vertices to make it appear like a bipartite graph and then show that it is one? All right, so try this on your own. And yeah, so hope you tried it on your own. The answer is yes. Okay, yes. Well, the way we could check is just literally trying to separate the thing. So let's put A in the x set. All right, that means B and D have to both be in the y set. Well, if D is in the y set, E, there's an edge from D to E. E must be in the x set. And no issues here, right? B is also in y. This edge is good. E is in x, so F has to be in y. And C has to be in x. Okay, and so now let's redraw our graph just so we can really see that all the edges go from x to y. So our x set is AEC. Our y set BDF. And there's an edge AB, AD. ED, EB, EF. And C has CB and CF. All right, and so now it's very clear. This is the same graph. it's very clear that this is a bipartite graph, right? There's no edges from x to x. There's no edges from y to y. So just because it's not drawn like a bipartite graph doesn't mean it isn't a bipartite graph. You might have to move things around a little bit to check. And it turns out there's a very easy way to check if something is a bipartite graph. So this theorem tells us how to check if we have a bipartite graph. So a graph G is bipartite if and only if. All right, so this is the only possible way this could happen. There are no odd cycles in the graph. Okay, so this says if you find an odd cycle in the graph, we automatically know it's not bipartite. All right, so let me give you an example. If I give you the graph that has 8 vertices, that has the following edges, all right, so suppose this is our graph. I automatically know it's not bipartite because I could find an odd cycle in it. So for instance here, this is an odd cycle, right? It's a cycle with 3 edges, and 3 is odd. Since I found an odd cycle, I know it's not a bipartite graph. I don't have to bother doing anything else. I could check automatically. Here, you could look for some cycles. They're all even, right? This square, that's a 4 cycle. If we go around that perimeter there, that's a 6 cycle. Both of those are even. All right, so if we could find an odd cycle, we automatically know it's not a bipartite graph. And so one type of bipartite graph that's going to be useful for us is called the complete bipartite graph. So let's define that, and we'll look at a quick example. All right, so here we have a simple, so no multi-edges, no loops, bipartite graph G. What does this mean? X, U, Y. This is the union symbol, which looks like the letter U. It's just saying we have our X set and our Y set. So our vertices are made up of an X set and a Y set. So a simple bipartite graph G is a complete bipartite graph. Okay, so remember what a complete graph was. A complete graph is when every pair of vertices has an edge between them. Okay, so what is a complete bipartite graph? Every vertex in X has an edge with every vertex in Y. So if every vertex in X is adjacent to every vertex in Y. All right, so that's what it means for a graph to be the complete bipartite graph. Okay, just continuing the definition, if the size of X is m, and the size of y is n, then we write remember k is for complete, and we're going to write m comma n. So this notation means we have the complete bipartite graph. Our x set has m vertices, and our y set has n. All right, so just one quick example. If we had k, let's say 2, 3, would be the following graph. Our x set would have 2 vertices. Our y set would have 3. And we would have edges, right? Each vertex in x has an edge with each vertex in y. So this is the graph K23. And one last theorem before we call it quits for today. The total number of edges in this complete bipartite graph so the total number of edges in KMN is, let me know in the comments. Okay, no cheating. M times n. All right, so here there should be 6 total edges. Right, 3 for the first one, 3 out of the second one. 3 plus 3 is 6. All right, and so yeah, we're going to be seeing some applications of how this complete bipartite graph could help us model some situations where we want to pair up 2 distinct groups. Okay, that's all I have for today. So let me know in the comments if you have any questions. Otherwise, I will see you in the next one. Take care. Bye-bye.